good evening friends. I hope all of you are able to see this. So what you have to see here is the velocity. Just have a look at these equations. They are all going to be handy in solving the numericals that we are going to handle now. Okay, so that's why I said these are all ready reckoners. Most importantly, you see velocity doesn't depend upon mass. The Bohr radius depends upon mass, that is R is inversely proportional to mass, and the energy of the orbit depends upon the mass. Energy is directly proportional to mass. Okay, and the transition, of course, will also depend upon the mass. So E is proportional to m, R is inversely proportional to m. So some things like that, you should be able to abstract from this data. Okay. So we will come to the first problem. Very interesting problem this is. I hope all of you can see the board clearly.
Yes, sir.
Yeah. Right. Too small? Okay, right. Okay.
Right.
So this is a very interesting problem. I think all of you have read this problem. Hello, everybody have read? Say yes or no.
Yes, sir. Yes, sir.
So in this problem, they have calculated the separation between the particle of a system in the ground state and the corresponding binding energy and wavelength of the first line in Lyman series if such a system is positronium consisting of an electron and a positron revolving around their common center of mass. So here you see I have just said what is this positron. I think in my question itself I have explained what is a positron to all of you. Okay, I suppose all of you might have read it. So you can see the diagram here, all of you?
Yes, sir.
So here you have an electron and a positron. See, electron and positron have opposite charges. That is, if this is E plus, it is E minus, it is E plus. The magnitude of the charges are same, and both of them have same mass. Okay, the mass of this electron and the mass of this positron is same. Only thing is charge is opposite. Okay, and they are revolving. See, they are both moving in this circle. Only thing is they are opposite on the diametrically opposite points. Okay, so that is called positronium, and there are statements like it will annihilate each other. That means it is unstable. After very short duration of time, these two will merge and become one. That is called annihilation. Well, that is not important for this problem. In this problem, what is important is you have a system where there is electron and a positron, and both of them are revolving in this circle like this. Okay, that is the system. And we have solved a similar problem earlier in mechanics. What is it? There are two masses which are revolving in the circle. Regarding stars, do you remember that? Some name was there.
Yes, sir.
What is that called? Two stars revolving like this. We have solved a similar problem. Okay, this is exactly similar to that. But only thing is here, apart from masses, they also have got the charges. Okay, now if you recall the discussion that we had when I was speaking about the Rydberg constant. Okay, anybody remembers? Hello? Rydberg constant, that is R suffix H for hydrogen, and for other heavy atoms it was R suffix infinity, and there I had also, the same slide was also shown, wherein when you calculate the RH, you will also consider the reduced mass. So when you reduced mass means, here you see the consideration is in the nucleus, the protons and electrons are not at rest. They are also revolving. Hello, are you with me?
Yes. Yes, sir.
They are also revolving. But when we are solving this numericals and all, we can put a condition that assuming they are at rest. We can put a condition. So if the protons are assumed to be at rest, then in the derivations that we have seen, we have taken the mass of the electron in our derivation. That is mvr is equal to nh by 2 pi. We have only taken the mass of the electron. And when we said, when we also discussed the electrostatic force, we have taken the mass of the electron. But frankly speaking, if the proton was also moving, then we had to take the reduced mass. Okay, what I mean is, in these derivations that you see here, this m, can you all see this here? R is equal to n square by z, bracket epsilon naught h square by pi m e square is equal to n square pi z r naught. I hope all of you can see this. Hello?
Yes, sir.
So this m is, we have said it is the mass of the electron in the system, in the hydrogen atom, hydrogen-like atom. But supposing the proton was moving, then this m will be what? This m will be equal to this value. Which value? The reduced mass. That m will be equal to me into mp divided by me plus mp. That is reduced mass. Instead of m, we have to put this value. Did you get it?
Yes, sir. Yes, sir.
So here you see, we have got a similar situation. We don't have a proton, but we have something like a proton, that is the positron, and it is in motion. Got it? We have something like a proton, but it is in motion. Therefore, the m in the above equation will now be equal to this one. But now in this case, both the masses are equal. So what will happen here? This will be m into m square divided by 2m. So that will become what? M by 2.
Yes, sir.
Okay, that will be m by 2. So that is what we call it as the reduced mass. That is what we call it as the reduced mass. Okay, then if you substitute, now coming to this formula here, in this case what happens? R will be equal to n square by z epsilon naught h square pi m by 2 into e square. Got it?
Yes, sir. Yes, sir.
Similarly, E will be equal to z square by n square. Instead of m, you will have m by 2 e raised to 4. Did you get it?
Yes, sir.
Okay? That is all. So, therefore now with this knowledge, we will proceed to solve this problem. I hope everybody got what I said.
Yes, sir.
If you have any doubt, you can ask. Om, did you get it? Om? Hello, what's wrong with students? Why have you blocked the mic and keeping quiet? Okay. He's left it. Okay, done. He's not there. Okay, I hope all of you got the theory here.
Yes, sir.
Fine.
Yes, sir.
Okay. So now we will solve this problem. Okay. So what is it now? Calculate the separation between the particle of a system in the ground state, the corresponding binding energy. Binding energy means see now the positron and the electron, or the positron and the electron are bound to each other. I suppose you are able to understand that, because the positron and the electron, the positron E plus and E minus, they are bound to each other. They cannot move away from each other, but they are moving like this. They are bound. And therefore, whenever they are bound, there is a concept of binding energy. Binding energy. Is that clear? There is a concept of binding energy. See, in the regular atom, you have the electron here, you have the electron here, and you have the proton here, positive charge, and this will be revolving around it. But in this case, you have this system which is revolving. So we said electron is bound to the proton. So electron is bound means the binding energy of this electron, what is it? It is minus 13.6 electron volts. Hello?
Yes, sir.
Huh. Now what we have to understand here in this situation is that this binding energy, if you see the formula for the binding energy, E is proportional to M. R is proportional to 1 by M. That's what we abstracted from the above this one. Got it?
Yes, sir. Yes, sir.
Huh. So in our case, what has happened? This M happens to be M by 2. E is proportional to M by 2. Okay? And R is proportional to 1 upon M by 2. That's all. Okay? So therefore, in this particular case, the proton is replaced by the positron. But it's a system which is revolving. Therefore, the binding energy. See, if the proton was there and the electron was here, the binding energy was this. The mass of this was M. Now the mass is 1 by 2. Therefore, what will be the binding energy here? What will be the binding energy? See, E is proportional to, gentlemen, see here, if E is proportional to M, then the binding energy is 13.6. Now what has happened in the new system? E is proportional to M by 2. Therefore, the binding energy will also become half.
Okay, sir.
Okay, so this will be minus 13.6 divided by 2. Correct? So 13.6 divided by 2 will go, okay, minus 6.8 electrons.
Yes.
Okay, that's how you have to solve this system. You have to solve the problem. Okay, so the first line, binding energy, and the wavelength of the first line of Lyman series. So Lyman series, it will go from N2 to N1, correct?
Yes, sir.
So N2 to N1. So can you find out the wavelength of the first line of the Lyman series here? In this case. If you are not understood, you can ask me, I will teach you. Come on, respond, speak to me, talk to me, all of you. Yeah.
Yes.
So, what will be this one? Somebody tell himself. The wavelength of the first line in the Lyman series. What will be the wavelength? What is the formula I will use? The wave number. Wave number is equal to R into Z square into 1 upon N1 square minus 1 upon N2 square. Correct?
Yes. Yes, sir.
So you can use that and you can get it, or you can do like this. See, now what you have got here is they are asking now the wavelength of Lyman. Lyman means from N2 to N1. Okay, so you have to find out now the difference in this energy level. The difference in this energy level. Did you find out? Hey, come on, yeah. See, if it was a hydrogen atom, then E1. If it was a hydrogen atom, it would have been E1 is equal to minus 13.6. Correct? And now what has happened? Because in this positron system, this is becoming minus 6.8 electron volt.
Yes, sir.
Okay. What is E2? What is E2H? E2H was what? Or E2 minus E1. E2 minus E1 for hydrogen. What was it? It was 10.2 electron volts. Correct now?
Yes, sir.
So what is now what is it going to become? It is going to become half of it. it is going to become half of it, no? Hey, in this case, mass is reduced, man. Are you not following? This is E. E will now be equal to E is proportional to M. In this case, the reduced mass E is proportional to M by 2. So this will also reduce to 50%. 5.1 electron volt. Got it?
Yes, sir.
And now they are asking you the wavelength. Okay, the wavelength. So wavelength, what will you get here? We used to use the formula 1 to 400 divided by E. Okay, so you will straight away write here 1 to 400 divided by 5.1 electron volt. So you will get the wavelength. See, this problem is asked in the examination. I have taken this problem. Okay, now don't say, okay, oh, there is an extraordinary theory for this. But remember, when I was teaching you the Rydberg constant, I did say very clearly that if the proton is in motion, then you have to use the concept of reduced mass. Is that clear?
Yes.
Now see, listen, all of you, you have to unmute your mic. Aram se sit as if you are sitting in the class and aram se discuss. Okay, aram se discuss. Don't be afraid. You if you put effort, you will learn. Huh? If you simply keep dumb there, you will not learn. Okay, shall I go to the next problem?
Yes, sir. Yes, sir.
Come on, be enthusiastic. Today both Region and Om are not there. Fine, they have solved the problems. Probably that is why they have taken off. See, if you have solved the problem, you send a message. Both of them have sent a message here. They have solved all the problem. Only in one problem they have difficulty. I will solve it for them. Okay, now try to solve this problem. Find the quantum number n corresponding to excited state helium plus ion. See, it is find the quantum number n corresponding to excited state of helium ion if on transition to the ground state the ion emits 2 photons in succession with wavelengths 108 nanometers and 30.4 nanometers. The ionization energy is so. So you study this problem and give me the strategy. If any student has got the strategy to solve this problem, please let me know. Feel free. I am training you how to solve the problems. All of you participate. Aram se. This is not to give you any shabashgiri if you have solved, and it is not to scold you that you have not solved. It's a learning process. I want all of you to learn. So you try to visualize this problem. Aram se. So in this problem, there is the ground state. Sorry, this is the n is equal to 1. So you know n is equal to 1 is the ground state. Hello.
Yes, sir. Yes, sir.
Okay. So the question is find the quantum number m corresponding to helium plus ion. So helium plus ion means what? Z is equal to 2. Correct? Z is equal to 2. That is basically what we have got. And it is a helium ion. Now there are 2 transitions that is happening to this. Correct? That's what is the problem. So helium ion, the transition to ground state, the ion emits 2 photons in the succession. In the succession, that word is important. One is 108.5 nanometer, other one is 330.4. That means there is some energy level n. We don't know what is that yet. So the electron would fall from this level n, some level n, to this level. And from this level, because they are called successive transition, it will fall to the ground state. Now, watch out students. This one is some n is equal to nth state. N is equal to nth state. We don't know what is that state. Okay, it can be, see, this is n is equal to 1. This can be n is equal to 5, 6, 7, 2, 3, anything it can be. I have just taken it as some n is equal to n. Okay? Huh? Huh. And this, say, if I say this n is equal to n1, then I will say this is equal to n is equal to n2. I don't know, some state. Are you with me, students?
Yes, sir. Yes, sir.
Okay. So this one, how much have they told is the energy of the first one? 108 and 30.4. So this is 108 and this is 30.4 electron volts. That is the energy emitted by the photon in these two cases. And finally,
Yes, sir.
it will come to this one. This is what is the data that they are given. Okay? They are, see, you should not say if this is 3, this is 2, and this is 1. No, we don't know. It's just that the electron will jump from this to this and from this to this. This is the data that they have given. Did you capture it, students?
Yes, sir. Yes, sir.
So they are now asking what? Find the quantum number n. First we have to find the quantum number n, and these are the two transitions that they have put. Okay?
Yes.
So how will you go about solving this problem? Sorry, this is wavelength they have given, no? Sorry, yeah, sorry, I made a mistake here. So this is not EV, this is nanometer, wavelength they have given. This is the wavelength they have given, not the energy. That is, the photon is coming out, the wavelength of the photon they have given. So from this data, you can find out what? You can find out delta E1. From this data, you can find out delta E1. What will be delta E1? 1 to 400. You remember? 1 to 400 divided by lambda. Standard formula.
Yes, sir. Yes, sir. Yes, sir.
So in this case, it is lambda. Okay. So what will you write here? 1 to 400. What is the lambda one here? 100. Excuse me. 108. Is it 108? 108.5. 108.5. Isn't it? Then I will get the value in electron volts. Am I right?
Yes.
Hello, everybody there?
Yes, sir.
No. See.
Angstrom.
Good boy. So this should be angstrom. So it is nanometer. Nanometer is 10 to the power of -9. Okay. So
Yes.
So multiply and divide by 10 to the power of -1. Okay. Understood? Then it will become angstrom. So it will become what is it? It will become here. It will become 180.5. No, 1805 angstrom. Nanometer is converted to angstrom. And if you divide this by this, you will get the value in electron volts. Got it?
Yes, sir.
Then what will be the next step? Don't sit down, gentlemen. Aram se speak. What will be the next step? See, it has jumped from here to here, and they have given this value. They have given the ionization of this. They have given this value. The energy level at this point is -13.6 electron volt. That value they have given. That is ionization energy of hydrogen atom there. So if they are given hydrogen atom, then this should be multiplied by Z square. That will be the energy level of this. Arey yaar, from here to here they are giving energy. One more photon is given in succession. So you can find out the energy of this, no?
Yes, sir.
What will be the energy of that? Delta E2 will be equal to 12400 divided by 30.4. Correct? So 30.4 nanometer will be 304 angstrom. So you will get this electron volt energy. So that means now from this to this energy they are given, from this to this energy they are given. And they have told for hydrogen it is 13.6 and they have told it is helium. So what will be the ground state energy level for helium plus ion? The ground state energy level for helium plus ion, E1 will be equal to 13.6 into Z square. and here z is equal to 2. Okay, so this will be 13.6 into 4. This will be the energy level. Got it?
Yes, sir. Yes, sir.
Now, what is the question they have asked? You have to find out what is n. You have to find out what is n. So now, if you add these two, you will get the total energy. Correct? This plus this, you will get the total energy. Say the total energy is delta E. This delta E, you will get it by adding this. Okay? And this is equal to 13.6 into z square. Z square is 4 into, it is coming down to the first state. What is first state? 1 upon 1 square minus 1 upon n square. It has come from n is equal to n1. Got it here?
Yes.
Okay? N1. So, from this formula, you can determine what is the value of n. Okay? And that is the answer.
Yes, sir.
Okay, everybody got it?
Yes, sir. Yes, sir.
Now, calculate the energy of hydrogen atom in its first excited state if the potential energy is assumed to be 0 in the ground state. So here you see again the ground, this is 0, this is the first state, n is equal to 1. Okay, now calculate the energy of the hydrogen atom in the first excited state. If the potential energy is assumed to be 0 in ground state. So the first excited state is this, n is equal to 2. So now they are asking you what is the total energy of this. What is the total energy of this? See, as all of you know, supposing the question was asked, what is the energy at this level? Supposing this is the atom, n is equal to 1. What is the energy at this
Minus
point?
13.6.
Thank you. Minus 13.6. What is the energy here?
Into 2.
Into 2. ಏನಾಗೈತಿ ಸುಶಾಂತ
Yes, sir.
ಎಷ್ಟು minus 3.4
Minus 13.6 by 2. Yes, sir.
minus 3.4 no
Yes, sir.
minus 13.6 by 4 4 है क्या? Is it not minus 3.4 electron volt?
Yeah, okay.
ಅಲ್ಲ generally hydrogen atom the level 1 is 13.6, level 2 is 3.4, correct?
Yes, sir.
Yes, sir. Now this total energy as you know, it is having both kinetic energy plus potential energy. I suppose all of you know this.
Yes. Yeah. Yes.
Now what is the relation between kinetic energy, total energy and potential energy? Total energy will be equal to minus kinetic energy, and this is equal to what? Potential energy by 2.
Yes.
I hope all of you remember this. ठीक है?
Yes.
Great. So now, what is the potential energy at this point? What is the potential energy at this point?
0.
0 ಮಾಡ್ತೀವೋ ಈಗ ಇನ್ನೂ 0 ಮಾಡಿಲ್ಲ.
Yes, sir.
ಈಗ
Minus 13.6.
minus potential energy will be what? Minus 13.6 into 2. See, the total energy is 13.6, no?
Yes, yes, sir. Yes.
Minus 13.6 into 2 is the total potential energy. Correct?
Yes.
So what will be this value? 2 6 are 12, 2 3s are 6 plus 1 7, 2 1s are 2. Minus 27.2 electron volts. What is this? This is the potential energy.
Yes.
Now, what they have told is, what is the total energy of this point if you consider this potential energy to be 0? See, you remember, potential energy is a scalar quantity, right? I hope all of you remember.
Yes.
See, that means now, say now, this is Earth, okay, and supposing I have a body here of mass m, okay, and height h. What is the potential energy of this body? mgh. I suppose all of you know that.
Yes.
Yes, sir.
The potential energy of this body is mgh, provided you have taken the potential energy at this point is 0.
Yes, sir.
Yes, sir.
Now supposing I will assign, because this is scalar thing, I will assign the potential energy of this point to be 10 units. Then what will be the potential energy of this point with respect to this? What is the potential energy of this point with respect to, see, if this is 0, this is so much.
MG plus
mgh plus 10. mgh plus 10. Got it?
yes, sir. Got it.
Huh.
Yes, sir.
So, understood now? Now, that means now you can simply add some numbers to this. You can simply add some numbers. See, I have added number 10 to this. So, I will add number 10 to this. That is what is the potential energy. Got it? Now, in this case, I want to make this energy, potential energy of this point 0. So, what should I do? I should add to this 27.2 electron volts to this level.
Yes, yes, sir.
Then this will become 0. Then the same potential energy I should add to this point.
Yes, sir. Minus.
So it is minus 3.4 plus 27.2 electron.
Yes.
Got it?
23.8. Yes.
23.8. Correct? I will go by you. Minus 23.8 electron. This is what? The total energy.
Sir, plus, sir.
Plus 22.
Yes, that's 20. Understood? This is a simple mechanism.
Yes.
You should know what is potential energy, then you can solve this problem.
Yes, sir.
Okay? So if you cooperate fast, then I can teach fast and solve 4 sums for you. Otherwise, God save you and me. See, all these problems you have solved in chemistry, gentlemen, more difficult sums. Okay, so you should be able to aram se handle. And if you say we have forgotten, God save you. Because whatever you have learned on the first day when you enter the college, you have to remember it till 2023 June. So you cannot say I have forgotten. If you have learned and if your learning has got converted to knowledge, then you will not forget. But if you have simply studied, then it is very volatile. So just be calm and cool and put your efforts and learn. Then it will become knowledge and permanently in your head. By solving sums, you will not get knowledge. Understand? First, if you have knowledge, then if you are able to apply that knowledge and solve sums, then you will enhance your knowledge and you will develop skills. So without having knowledge, if you are solving module sums, God save you. You are simply wasting your time. So please, aram se, enjoy these classes. Don't put pressure of any examination on your head. This one. Wavelength of the first line of Lyman series in hydrogen is identical to the second line of Balmer series for the same hydrogen-like X. Hydrogen-like ion X. Calculate the energies of the first 4 levels of X. I think you should be able to tackle this.
Yes, sir.
At least somebody told yes, sir. Good. Will you solve?
Similar, that's all.
You have solved this?
Chemistry is similar, that's all.
Similar. Then you fatafat solve this, man. Make me happy, man. At least for a change. So the first line of Lyman series means it is from n is equal to 2 to n is equal to 1. For hydrogen, is identical to that of second line. That means from the first data, what will you get? The energy of that will be 10.2 electron volt. That's how we are going to handle it.
So we can use Rydberg's formula.
You can use Rydberg formula and do it. That's the better way. That's a better way to do it. Correct. So that should give you a hint. That is 1 upon lambda 1 will be equal to Rydberg into Z square. So Z square for hydrogen is Z is equal to 1. Still I am writing this. Upon 1 square minus 1 upon 2 square. So this is So this is the first thing that you get here. And here z is equal to 1. So you get here r into 1 minus 1 upon 4. Okay. Then the second data they have given is what? Is identical to the second line of the Balmer series for some hydrogen-like atom.
Yes.
So I will consider the next wavelength here to be 2 and here R, but they have told it is hydrogen-like ion. So I don't know how many, what is that ion? It can be helium, lithium or anything. So I will simply use Z square there. And second line of Balmer. So second line of Balmer means this should be 2 square and this should be 4.
Okay.
4 sir.
Yes, sir.
So this is the data that we get there.
We can relate these two.
Yes, and they are told these two are identical. Okay, so these two are identical. So these two are identical. So I can write here 1 by lambda 1 is equal to 1 by lambda. Correct? And therefore, if I write this is equal to this, then RR will cancel, and
Yes, sir.
RR will cancel. Then you
We
get
get Z is equal to 2.
That is 2, sir.
yes, good. So this will imply that you get value is 2. Okay. Once you know the value of Z is equal to 2, then energy of the first 4 levels
Yes.
of X.
Yes, sir.
Energy of the first 4 levels of X. So here first 4 levels of X means one is R into Z. Z is 2. So 4R. 4R into 1 upon 4 minus 1 upon 9. Correct? First one. Calculate the energy. Sorry, they asked energies. They are asking energies. Okay. So energies you have to use 13.6 into Z square. Z square is 4. 1 upon 2 square minus 1 upon 3 square. 4 levels they are asked. So like that you have to go on writing this and get the 4 levels of answer. Is that clear?
Yes,
all of you?
Yes, sir.
Yes, sir.
Yes.
For a change, many students said yes. Please, don't put pressure of any examination. Then you will not learn. You will unnecessarily get stressed out and everything will go to dogs. So no excuses. Just be calm and cool and enjoy learning. Till October, your job is only to learn and enjoy learning. That's all. After that, we will plan for the examinations. Of course, we are doing sums which will lead to examination. But I want you to learn. I don't want you to be under pressure. Okay? Fine. Doubly ionized lithium ion. That means 2 electrons are knocked off. Lithium is a hydrogen-like atom with atom number 3. Find the wavelength of radiation required to excite the electron in lithium 2 plus from the first to third Bohr orbit. From the first to third Bohr orbit. Quite simple. I think you can do it orally also, right? It will be 13.6 into atomic number is 3. So it will be 13.6 into Z square. Z square will be 9. 9 into 13.6 into bracket wavelength to excite from first level. That is 1 upon 1 square minus 1 upon 3 square.
Yes, sir.
Correct? So that will give you 1 upon lambda. That will give you 1 upon lambda. So the wavelength necessary to excite it, you will get from this formula. Those of you who are not telling yes, you are wasting your time and my time.
Got it, sir.
But other students are not telling yes. So R into Z square into 1 upon 1 square minus 1 upon 3 square.
Yes, sir.
Yes, Aniket is active. So this is so you will find out the wavelength from this. Okay. How many spectral lines are observed in emission spectrum of the above excited system? So that means now the electron is jumped from n is equal to 1 to n is equal to 3. How many spectral lines when it comes down? How many spectral lines will you observe?
3, sir.
3 is it?
Yes, sir.
3, because from n is equal to 3 to 2, 2 to 1, and from 3 to 1 directly also it means.
Yes, sir.
So you can observe 3 spectral lines. Okay?
Yes, sir.
Right. One more problem we'll solve.